Lab 1B, when did we finish Lab 1B? Thursday? So it'd be due Thursday then. Okay. Was it Thursday or was it Tuesday?
Which? I'm confused. Oh, the one where we measure the
Yeah.
crystal at the end?
The sulfate.
This, do we finish it Thursday? Yeah.
We finished
we
it
did
Thursday?
finish it
All right, then it'll be due Thursday, 1B. 1B, though, I wanted you to do an extra calculation, but we could do that in lab. So I have to do that.
All right. When we think about light and energy, let's just start off with infrared here and look at the visible. Visible is going to consist of red, orange, yellow, green, blue, indigo, violet. And then once you go beyond violet, we get into ultraviolet. But what happens is when you have an electron, in a piece of matter, and we shine light on it, the electrons can get excited in the matter. So we can excite the electron, let's say, up to infrared energies. There are different ways to excite the electron, but essentially you just put energy in from the surroundings. The energy that you put in from the surroundings can be either light or it could be kinetic energy, that is heat or whatever else. In other words, what we want to do is we want to excite the electron to a higher energy. The electron doesn't stay there forever. The electron gets excited here, and eventually what's going to happen is it's going to drop back down. And so if an electron gets excited to this level, it'll drop back down. And we call this an excited state here. And down here we call this the ground state. When the electron drops down from the excited state back down to the ground state, then it has to emit energy. So we're going to emit energy. And the energy is usually in the form of light in this case. And so we could excite the electron not with light, but we can excite it with heat, for example. So if we were just to heat up this up. If I heat it up a little bit, it doesn't look hot, but it is hot. You can feel it. That's infrared energy being given off. So I'll just excite the electrons. In this case, excite them a little bit. The electrons go up here and then drop back down. But what happens if I excite the electrons a little more, with the flame? If I excite it, it'll start to glow. Red hot. This is red hot here. Obviously, you don't want to touch it. It's red hot metal. But red hot metal, do you see it's emitting light? Emitting light. And so that's just exciting it to a little higher energy until we get into the red. And so we get the electron excited up here. It doesn't stay there forever. Eventually it's going to drop back down to the ground state and emit red light. And so we have a red hot piece of iron. We can continue exciting this. In fact, the hotter and hotter this piece of metal gets, let's see. Okay, so that's red. And then do you see the orange? Orange. And as we start mixing the higher and higher energy colors, what we're going to see is that eventually this will glow. What color? White hot. Yeah. White hot. And so I'm just exciting it. And when you see white, what is that? That's all the colors of the rainbow. In fact, what we call that, you know, when you see all the colors in the rainbow, what we see is a continuous spectrum or a continuum of colors. With this continuum, are there any colors missing? If you see white light, are there any gaps in there or anything? No, it's just a continuum of colors. And eventually, if we excite it enough, we'll go past violet into the ultraviolet, and we'll see. Continue there. An object like this piece of metal that behaves like that is called a black body. Black body. Because black bodies, what do the black bodies do? If they're black, then that means they absorb what colors?
All
Well, yeah, all of them. And so black bodies absorb all colors. In other words, they're going to absorb the whole spectrum, and that is the whole rainbow spectrum or the continuum, or the continuous spectrum. If they absorb all colors, then what that means is the electrons are going to get excited to all levels. And when the electrons get excited to all levels, they'll start to emit all colors of the rainbow. And we call that a black body emitter. Black body emitter will start off, emitting infrared, and red, and orange, and then you start adding in all these colors, and it becomes more and more white until you get white light being emitted. So we should see. So a black body emitter is going to emit the full continuous spectrum or continuum of colors. Eventually, we'll get to ultraviolet, and then black bodies should start emitting ultraviolet light. This is what physics predicted. We call it classical physics because. So here's an example of a black body. This is molten iron. Molten iron's got a lot of electrons. Those electrons get excited, And so some of the electrons are excited low energy. Those are emitting infrared. But you can see here it's white, and therefore we see all the colors of the rainbow here being emitted. It's a continuous spectrum of colors. So this is a black body emission by molten iron. You can make a light bulb out of this, but it isn't going to be very practical. So is it just heating that paper clip, which is just a iron wire? This is what it looks like in terms of the spectrum. Visible light ranges from what to what wavelength? Nanometers here. It ranges from
290 490 to 700.
Yeah, or 390 nanometers to 760. So visible light's in this region here. Above 760, we have what kind of light? Infrared. And then below 390, we have ultraviolet. And so this is infrared. And so it depends on how hot you heat the piece of metal. This is black body radiation. Radiation just being the light that comes off.
Professor, why is it that it goes red, then orange, but it skips all the other colors?
It doesn't skip. It doesn't skip those other colors. Those other colors are there, but when you mix red, orange, and yellow, what color does it look like? It looks like orange. When you mix red, orange, yellow, green, does it look green? No, it looks kind of orange.
Layered on top.
Yeah, you have to combine all the colors because there's so many electrons there and they're emitting all the colors. So let's say you topped out at green. Well, it's not going to look green. It's just going to look like a different shade of orange. And then you just keep adding the rest, and eventually it just becomes more and more white light.
And so that's why you don't see, I mean, when you go back here, you don't see the blue and the green. I see red, and I see orange, you know, and yellow, but as you start combining the colors, it doesn't add up that way. And this is what you see here. Actually, this is showing intensity, you know, how bright the light is versus the wavelength. And this is the temperature, let's say the temperature of the molten iron, 5,000 Kelvin, 7,000 Kelvin, or something, the black body. And so here, if we heat this to 5,000 Kelvin, which is well, 5,000 Kelvin, and we start emitting light, you see mostly visible light here, some infrared, maybe a tiny bit of UV here. As we get the object hotter, you know, start to shift it to, you know, higher energy colors like blue, violet, a little bit of ultraviolet's being emitted. And then we can continue heating it up. But what happens is this. As we continue heating this up, the UV emission isn't what's predicted. You know, what's predicted would be based on these lines here, as far as the emission goes. And what happens is the higher energy emissions here are much less intense than what's predicted here by the excitation of electrons in what we call classical physics. And so this problem here is called the UV catastrophe. And the UV catastrophe was that the emission in the UV wasn't as predicted based on exciting the electrons and letting them drop back down from the excited state to the ground state. And so what happened was they tried to fit the emission behavior to some mathematical function. And they were able to fit this emission behavior to a mathematical function. And the mathematical functions, it's just not any mathematical function, but it's a mathematical function trying to relate the physics of this. And so what happened is that the mathematical function that they related this to had to have the energy do something funny, and that is the energy had to be discontinuous, like matter. Now, what do you mean by discontinuous? Because if the energy is discontinuous, does that mean that the light is discontinuous? In other words, if you have a rainbow, is the rainbow a continuous spectrum of colors or a discontinuous spectrum of colors?
Discontinuous.
A rainbow is, oddly enough, a rainbow is a continuous spectrum of colors. This is not discontinuous. What is discontinuous is this. In order for the UV catastrophe to be fitted mathematically, this is how they had to make it discontinuous. So let's take red light. Red light's at 760 nanometers. What they mean by red light is that this. Now there are two ways we look at energy here. We look at the energy of the red light, and the energy of the red light, we cannot have any energy we want. The energy of the red light is going to be discontinuous in the sense that red light comes in packets. And these packets are called photons of 760 nanometer light. And the photon, the energy of the photon is given by this equation. The energy of the photon is just related to its frequency times h. H is Planck's constant, that guy there.
where H is equal to 6.626 times 10 to the minus 34 joules times seconds. Nu is the frequency of the light, and we could also relate it to the wavelength, H times C over lambda, C being the speed of light, lambda being its wavelength. And so this is what's meant by discontinuous. It's like this, you know. When we think about mass, well, mass is a little bit tricky, but when we think about mass, is it possible to weigh any amount of sugar you want?
Not minuscule.
It seems like, yeah, you should be able to weigh any amount of sugar you want, but it turns out that the mass of sugar is discontinuous in the sense that when we get to very, very small masses, then it's not possible. So let's say I wanted to weigh out 190 U worth of sugar. Let's go 190 U worth of glucose. It's my sugar. Is it possible to get 190 U worth of glucose? No, it's not possible because a glucose molecule weighs, let's say, roughly 180.2 U. This is the average. We probably aren't going to find the average because of isotopes. But if a glucose molecule, a single glucose molecule weighs 180.2 U, this would be for one glucose molecule, then it's impossible to get 190 U because the next allowed mass would be 2 times that, right? And so I could get 180.2 or I could get 360.4 U. And so this is what's meant by discontinuous. There's going to be a big jump. I could have one molecule or I could have 2 molecules, but I can't have 1 point whatever or a fraction of a molecule. It just doesn't work that way. Well, if I'm looking at the energy of red light, then the energy of the red light is going to be discontinuous in the same fashion. That is, I could have one packet of red light, this packet, which we call a photon, a packet of light. Well, I could have 2 packets, 3 packets, 4 packets, but I can't have like 4.5 packets. And so the size of the packet is going to be given by this equation here. It turns out that depending on the wavelength, we'll have different size packets. And so a packet or a photon of violet light at 390 nanometers is going to be different. And so can you calculate the energy of a photon for violet light and the energy of a photon for red light? Here. Go ahead and use the equation there and calculate that, and then we'll talk about that.
It is -1. And it's not 6 points, it's 6.6.
6.1.
I thought it was a 6. So 50/50. For the wavelength, that's C is just what?
Yeah.
What's the speed of light? I really don't.
Speed of light is 2.997 times 10 to the 8th meters per second. Oh, is 0 for H? It's not joules per second, it's joules per second.
Yes, times.
Yeah.
Joules per second.
I heard you say joules per second.
Well, that's what I said too.
Alright, we're just looking at.
So, first
So for UV, I got 2.58.
Violet and red. I mean, no.
No.
Is that 390? Yeah, 390.
He's asking for
violet and red.
and red, yeah.
Just get a nice
Oh,
one.
over
here. The green is what?
2.997 times 10 to the 8 seconds. Just zeros per second.
What about tomorrow? When I take over the planet, I'm out. Oh, it's 2.9979.
I'm out for it. I
That was pretty smart.
All right, so what did you guys get for the energy?
Because, I mean, that.
Like 2.6 times 10 to the negative 19
Oh,
joules.
give me some more. 2.6
613.
613 times 10 to the negative 19
Yeah.
joules. Okay, thanks.
Also red.
Red light at 760 nanometers has a packet that has 2.6 times 10 to the minus 19 joules worth of energy. So can I get, let's say, 3 times 10 to the minus 19 joules worth of red light at 760 nanometers? The answer is no, I can't. I can get 2.6, and the next amount of energy of red light I can get at 760 nanometers would be 5.2. But I can't have 3, because that would have to break a packet into a fraction of a packet. We can't. The smallest amount of energy is this little packet. How about at violet? What's the size of the packet here? 5.96?
093.
5.093 times 10 to the minus 19 joules. Okay. So let's compare. When I compare red to violet here, the violet is about twice as much energy. And so we're going to have twice as much energy here. So the packets are going to be larger packets of energy. And so the photon here being twice as much energy, then I couldn't even get the same. If I try to get, is it possible to get 2.6 times 10 to the minus 19 joules of violet light? It's impossible, because I can't take a photon and divide it in half. This is the smallest amount of energy. And so red, yes, but violet, no. And so this is what's meant by it being discontinuous. And the energy of this light is discontinuous because I can't have any amount of red. And the same thing, I can't have any amount of violet. And so it's discontinuous in this way. Discontinuous. When it's discontinuous, we call it quantized. Like matter. Matter is quantized. This is because it comes in packets of matter, like a glucose molecule, 180 U. But if energy is quantized and is discontinuous, is the rainbow quantized and discontinuous? No, the rainbow is continuous. And so what that means is this. That means I have a the packet, let's say I went from 760 to 760.01. If is 760.01, well, actually I shouldn't go that way because that'll throw me into IR. Let's go to 759.9. If I went to 759.9, is that okay? Yeah. What if I went to 759.99? Is that okay? Yeah. In fact, I could go to anything, 759.99999 nanometers, and all that's going to happen is the packet of energy gets a little bit bigger. And so what we see is that we see this. There's a continuum of packet sizes. And so all I'm doing is I'm going from this size to this size, and there's no discontinuity there. It just gets a little bit bigger, a little bit bigger, a little bit bigger until I get here, as far as visible light goes. And then if I go into ultraviolet, it gets a little bit bigger. And so I have a continuum there, but when I look and I pick an individual color, let's say I pick yellow at this wavelength, then it's discontinuous, as far as how much energy of yellow light I can have. And so on one hand, it's what we call quantized. On the other hand, it's continuous. Continuous and not quantized. We could see this in the photoelectric effect. What implications this has. And in fact, this is how the photoelectric effect was described by Einstein later on. Heinrich Hertz, light striking the surface of certain metals causes ejection of electrons when the frequency is greater than nu naught, which is the threshold frequency. The number of electrons depends on the intensity of incident light. Kinetic energies of electrons depend on the frequency of the light. And so it's not so clear here in this slide, but there are two types of energies we look at when we're dealing with light. Two types of energy, thing. One is the photon energy here. And so let's say a violet at 390, the photon energy, I'll just do it to 2 sig figs, keep it simple. 5.1 times 10 to the minus 19 joules per photon. So a single photon has that. And down here, red, the photon energy is like 2.6 times 10 to the minus 19 joules per photon. Photon energy. And then I have the total energy. The total energy is going to be n times the photon energy. N times the photon energy here. And then I'll have the photon energy when I think about photons, it's awfully small. So, the same thing. When we think in terms of the mass of a molecule, it's awfully small. Do we usually work with just one glucose molecule, or 2 glucose, or 3 glucose molecules? Not normally. We normally work with a mole. In fact, this would be wrong. I shouldn't use the average for a single molecule. I should use the isotopic mass. And so another way of thinking about it is the photon energy per mole. Photon energy per mole of photons. And so if I have a mole of photons, then it would be 6.022 times 10 to the 23rd times the energy of that photon. So that's the number I have. And so what is the photon energy per mole for violet? And so let's just say 5.093 times 10 to the minus 19 times 6.022 times 10 to the 23rd, we get what?
$306.7 kilojoules per mole.
306.7
kilojoules per mole.
kilojoules per mole. All right, 306.7 kilojoules for a mole of photons. And for red light, what does it come out to? At 760.
It's 157.3.
157.3 kilojoules per mole. About half. Do you see that? But it has about half the energy. So 157 versus 307 roughly. Kilojoules per mole. And so let's try to visualize this. What's the difference between like a 10-watt light bulb and a 100-watt light bulb? Think. 10 watt is a lot dimmer, right? 100 watts a lot brighter. That brightness is called intensity. Right? Intensity, so let's look at 100 watt. 100 watt, do you know the definition of a watt? A watt is a joule per second. So 100 watts would be 100 joules per second. And it's different. Let's say I had a red light bulb at 760 versus a violet light bulb at 390. So this is 100 watts. We'll do it violet at 390 nanometers. Then what that means is I have 300 joules worth of photons per second. If I have 300 joules worth of photons per second, then I know the energy. What was the energy again per photon? It's like
5.1 times 10 to the negative 19 joules.
All right, we'll just do it like that. 5.1 times 10 to the negative 19 joules per photon.
Yeah.
And so if I have 300 joules per second of violet light at 390, how many photons per second is that?
.88 times 10 to the 20.
Times 10 to the 20 photons
Yeah.
per second.
Per second.
All right, now let's do a 100 watt light bulb of red at 760 nanometers. And so if I could make a light bulb that only emitted red light at 760, I'd have, oops, what am I doing, 300? Did I do 300, sorry. It's supposed to be 100 joules per second. Can we redo that? Sorry about that.
1.96.
1.96. So let's take a 100 watt red light bulb. 100 watt red light bulb is going to emit the same 100 joules per second. And so both of these light bulbs are emitting 100 joules of light per second. And so the total energy, what we call the total energy, is the same. And so total energy is the same. If the total energy is the same, what's the difference then? What's the difference is the energy of the individual packet or photon of light. That's different. We know that red light has half the energy per packet or per photon. And so what that means is that we're going to have a lot more photons to add up to this energy. And so we should have maybe twice as many photons roughly. So a photon of red light at 760 has what energy? What was it?
613. 613, 2.613.
2.6? Okay. 3 times 10 to the minus 19 joules. We won't do so many sig figs. And so this is going to give us how many photons per second? Well,
Three 3.84.
3.84
Times 10 to the 20.
times 10 to the 20. So we're going to need twice as many photons to add up, roughly twice as many photons to add up to the same intensity. And so this is the way we can visualize the light here. If we have violet light, violet has a shorter wavelength. And so look, we're going to go with 100 watts of violet light. And so the total energy is related to this, what we call amplitude, A. Amplitude is related to total energy. And so we kind of want these to have the same amplitude, or same total energy. The difference is that in order to do that, we have frequency. Frequency is going to be related to the energy of the photon. And so the energy of the photon, well, this is higher frequency, so we have more energetic photons. Okay. This is lower frequency, so we have lower energy photons. And so lower energy photons, we're going to need a lot more lower energy photons to add up to the same energy as this. So these are a lot smaller, these photons. And so we need a lot of these little photons to add up. Okay. And so we can see that here. Actually, not a lot. These are just half the size, so we need twice as many. To give us the same kind of amplitude. What's that? Now, let's go back to this. So they're talking about two different things. The intensity is related to the amplitude, which is related to the total energy. And then they're talking about the frequency. The frequency is related to the photon energy. Energy of the photon. So this is what Einstein won the Nobel Prize for, that electromagnetic radiation light has particle-like properties. Particle meaning it comes in packets, like matter. This is the energy of the photons equal to H nu. And so basically, this is what the photoelectric effect is doing. We shine light on a piece of metal, like potassium metal here. And, that light can excite electrons. And if there's enough energy, it'll excite electrons right off the metal.
Let's try that. So if I have some potassium solid here, and then I'll shine light on this. Let's shine like 5 watts of violet light. If I shine 5 watts of violet light, the violet light comes in, strikes it, and ejects electrons off the surface. Yeah.
So there's enough energy in violet light to knock electrons off potassium. Potassium is very easy to knock electrons off of. It's so easy to knock electrons off potassium that air and water can do it. And so this is why it's kept in an evacuated chamber. If there's air in here, it would totally corrode the potassium metal. If there's any water vapor in here, it would totally corrode the potassium metal. And so it's protected. Yeah.
Well, what if I shine 5 watts of red light on this? If I shine 5 watts of red light,
Well, that's the same total energy. It's 5 joules, right? 5 joules per second. And so I have this same energy. And so, you know, if I have the same total energy, shouldn't the same thing happen? So same total energy, 5 watts of red light, but nothing happens. Nothing happens. And so, if nothing happened with 5 watts, then maybe let's increase it. Let's go up to 100 watts. If I do 100 watts of red light, what do you think will happen? That's 100 joules. That's 20 times more energy per second. Is anything going to happen? It'll probably get warm, you know. Potassium metal's going to start to get warm, but no electrons are ejected. And so let's give up on 100 watts. Let's go to 1,000 watts. If I go to 1,000 watts of red light, still nothing happens. And that's 1,000 joules per second, which would be 200 times more energy than violet at 5 watts. 200 times more energy, and still nothing's happening. But still nothing's happening because when we talk about energy of light, there are 2 ways of thinking about it. One is the total energy, which is the amplitude. And so the 5 watts of violet light has very low amplitude, very low intensity. Right? So this is like a small wave. Yeah. But when I do 1,000 watts of red light, that has a very high amplitude. It's like a tidal wave. And so 1,000 watts is going to have like 200 times the amplitude. A lot more energy. But that's the total energy. The other energy I have to look at is the energy of the photon. The energy of the photon is going to be related to frequency or wavelength. And so it turns out, even though I have 5 watts of violet, the photons of violet are big in terms of energy. And so, let's just do that. Photons of violet are big. And so this consists of not that many big photons. Whereas the photons of red are small in terms of energy, so we got lots of little photons here. And those little photons all add up to a big energy. 1,000 watts is big energy. But the problem is this. The analogy here is like the red light would be like ping pong balls. These photons would be like ping pong balls. Individual ping pong ball can't do much damage, right? And so if you're hit by one ping pong ball, does it hurt? No. If you were hit by 10 ping pong balls, would it hurt? Not really. 1,000 ping pong balls? Not really, right? Not really. Whereas the violet would pack more of a punch. You know, violet would be like lead shot, you know, or lead balls. If you were hit by a lead ball, would it hurt? Yeah. Even if it's just 1 or 2 lead balls versus, you know, 100 ping pong balls, there's no comparison, right? Even though the total energy is the same. So if you look at the total energy of 1 or 2 ping pong balls and compare that to the total energy of 1,000, well, the total energy of 1,000 would be much greater. But individually, they don't do much damage. Does that make sense? And so the reason why even bumping up to 1,000 watts of red light doesn't do anything is because those ping pong balls aren't energetic enough to knock an electron off, whereas a violet photon is energetic enough. So if I increase the amplitude, let's say I went from 5 watts to 100 watts. If I went to 100 watts of violet, what's going to happen? If I go to 100 watts of violet light, I'm going to eject a lot more electrons. A lot more electrons will be ejected.
Will that potassium become unstable?
Oh yeah, potassium is going to become unstable. Very unstable.
Is that kind of how lasers work? Or that's different?
Well, lasers, we're looking at the intensity. You know, this is not really how lasers work in this sense. This is just knocking electrons off. This is how the photoelectric effect works. Photoelectric effect. So the intensity is, you know, how many watts. And so the number of electrons depends on the intensity. As long as the, actually you still might get 0, you know, as long as you have enough energy per photon to knock an electron off. And that's where this comes in. Kinetic energies of electrons depend on the frequency of the light. Well, the kinetic energy, what are they talking about there? They're talking about this. There's a certain minimum energy required to knock an electron off. And so if we don't have it, red's not enough. But once we get to blue, let's say, when we're in blue, it's enough. So this is called the threshold frequency. So for potassium, blue light is enough. But green won't do it. And so we get a certain, and it has to be a specific wavelength of blue that will do it. But violet is more than enough. Right? If we have violet, what happens with violet light is that not only does it kick the electron off the surface, but it gives it an additional kick of velocity. And so the higher the energy, the faster that electron is when it gets kicked off the surface. And so here. And so here, if we have a H nu is the symbol for a photon. If we have a photon here, if it's red, it's not enough, but if it's blue, it's enough. If it's violet, it's more than enough. So violet comes in here, it ejects the electron faster. So photoelectric effect is used in common applications like photodetectors, photosensors, that kind of stuff. So let's take a look at a problem here. From the homework.
Number 18 there. The minimum energy required to cause photoelectric effect of a potassium metal is 3.69 times 10 to the minus 19 joules. So what was the red light at 760? That was 2.6 something? 2.6 times 10 to the minus 19 joules, not enough. Violet was 3.8, roughly. 3.8 times 10 to the minus 19 joules. So violet's enough. Violet's more than enough because we only need about 3.7, right? And so let's answer the first question. Will photoelectrons be produced when visible light shines on the surface of potassium? If you shine visible light on the surface of potassium, will it eject electrons? Well, it depends what they mean by visible light. Do they mean all colors, or like, say, for example, if you're in a dark room, you know, with one of those red light bulbs, have you seen those photographic dark rooms? If you're in a dark room with a red light bulb, will the photoelectric detector work with a red light bulb? No. Red light's not enough. You're going to need, well, 3.69 times 10 minus 19 joules is around blue. You're going to need around blue light minimum to eject electrons of potassium. And so as long as the visible light is blue, indigo, or violet, you should probably be okay. If 520 nanometer radiation is shown on potassium, what is the velocity of the ejected electrons? So what is 520 nanometers? What color is that? And so let's look at the spectrum here. Roy G. Viv. Violet is 390, red is 760. So it's about 800 to 400. And so we'll go 500, 600, 700. So divide it into quarters. So 400, 500, 600, 700. So where is around 500 nanometer light roughly? 500 nanometers around blue. So it's probably okay. Blue, it's okay. It's shown, what is the velocity? Okay, so what we have to do first is we have to calculate what is the energy of 520 nanometer. What is the energy of the photon? Okay. And then once we get the energy of the photon, is it greater than 3.69? If it's greater than 3.69 times 10 to the minus 19, then we have more than enough energy. And any extra energy is going to be used to give the electron a little kick. And so why don't you go ahead and calculate. Calculate the energy of a photon at 520 and then see how that compares to 3.69 times 10 to the minus 19 joules.
It's over 9,000. That's what we calculated in the anime. In the anime, the yellow wavelength. That's what they do. Super saiyan wavelength. Oh wait, which one did we do? I'm actually understanding this.
3.81.
So was it enough energy? What was the energy of it? Photon.
3.81
3.81?
times 10 to the negative 3.
Okay, so we have more than enough. In order to eject an electron, it requires 3.69 times 10 to the minus 19 joules. So 3.69 times 10 to the minus 19 joules will eject an electron. If we have more than that, we had 3.81. Is that right?
Yeah.
Then we have excess energy. How much excess energy do we have? Well, let's see. 2.12 times 10 to the minus 19 joules. Is that right? All right, what that excess energy is going to do is it's going to give the electron a little kick, you know, like out here. And the harder the kick, the faster the electron will be ejected off there, or you know, the higher the velocity we'll have when it's ejected. The velocity or speed is given by this equation. It's the energy is equal to 1/2 mu squared, where u is the velocity. So the velocity of the ejected electron depends on the energy. The more energy you kick off of it, the higher the velocity. So it's going to be 2 this is kinetic energy, EK, divided by m. We'll take the square root of that. The mass of an electron is, what is it, 9.11 times 10 to the minus 31 kilograms. Is that right? 9.11. So go ahead and calculate the velocity that the electron's going to be kicked off there. Excess energy.
For E, is it the difference or is it
What's that?
the total?
This is the total energy. This is the energy of the light. This is the energy of the photon.
Negative. It's 'cause you have to switch to-
Then this is the minimum energy required to knock the electron off. And therefore, we're going to have a little bit of extra energy left over. Does somebody have the velocity?
I'm still confused, so EK is which energy again?
Oh. Here. So essentially, this is what we have. We have 3.81 times 10 to the minus 19 joules of energy coming in here. To kick off the electron, we subtract 3.69 times 10 to the minus 19 joules from that, which means that there's going to be excess energy here. The excess energy is going to be 0.12 times 10 to the minus 19 joules. So if we have excess energy, what that is, it's going to kick the electron off. The more excess energy we have, the harder the kick behind the electron is.
So the excess.
And so all we're going to do is we're going to convert this excess energy into kinetic energy for the electron. The kinetic energy is just 1/2 mu squared. And so we're just going to figure out what the velocity is. The more excess energy, the higher the velocity the ejected electron is. Right? And so, so we're just going to use this equation to calculate the velocity, and the velocity comes out to what?
1.679 times 10 to the 5 meters per second.
167,500 meters per second. It's fast. Yeah. 167,000. And so the electron's going to get kicked off with pretty high velocity. And the higher the energy, let's say I shine a UV photon on this. UV photon packs more punch. And so what's going to happen is the UV photon comes in here, it's going to require 3.69 times 10 to the minus 19 joules to knock it off. And then there's going to be a lot of excess energy, and so the electron's going to be ejected off at a higher velocity. Does that make sense? And so this is a photoelectric effect. Let's say I didn't have enough energy. If I don't have enough energy, then no electron's going to be knocked off. Like the red photon. The red photon is only like 2.6 times 10 to the minus 19 joules. Not enough to knock off an electron, right? We need 3.69 times 10 to the minus 19 joules to knock off an electron. And so that's all this graph is showing. We'll ignore this graph here. We're going to take a look at this graph here. This graph shows that the higher the frequency, that is, energy is directly proportional to frequency. So energy is equal, the photon's equal to h nu. So the higher the energy, the faster the velocity of that electron that's ejected off. And so as you get higher and higher energy, the electron gets faster and faster. Here, this is the minimum energy, or the threshold energy that we call it. Threshold energy, any energy below this, so all this light does nothing to it because it just doesn't have enough punch to kick the electron off. In terms of the math, this is it, in terms of the math, they do all this. Does this look easy to follow?
I don't know what those mean.
What's fee?
What's fee? Fee is given a name. That's called the work function. The work function is the minimum energy required to knock an electron off. So phi is 3.69 times 10 to the minus 19 joules here. And so if the photon energy has to be a minimum of 3.69. Any extra energy will be converted into kinetic energy of the electron. And so the only equation you have to worry about is this one right here, which just shows that if the photon doesn't have enough energy, then we aren't going to be able to knock off an electron. The math of this, I don't know, it's so convoluted. And this is the correct math, but physically, it just means that do you have more? If you have less, then what's going to happen? Nothing. If you have just the right amount, you'll knock an electron off. If you have more than the right amount, you're going to knock the electron off, plus give it some velocity. So if you have more than enough, you're going to knock the electron off, which is phi, plus give it some velocity. That's all this is showing. Physicists like to use different units for this. Chemists will have phi in joules. Physicists will have it in a different unit called an electron volt, which is a coulomb times a volt, which is a joule anyway, but they use electron volts. Anyway, let's continue on with this here. All right, so that's the photoelectric effect. We'll look at one more example because the energies are confusing to use sometimes. Right now, we're keeping it simple. We keep it simple here because we're just looking at the energy per photon. Okay? But sometimes it's a little bit more complicated, but let's take a look at an example where we're going to look at some bonds. These photons can be used to knock electrons off. These photons can also be used to break bonds. Let's take a look at some bond energies here. Compare.
Do you remember the energies in kilojoules per mole? What's red light in terms of kilojoules? It was like, it's 157 kilojoules per mole, right?
Yeah.
And the violet was like 380,
306.
306 kilojoules per mole. Okay, thanks. So let's look at some bond energies. So for example, if I have an OO bond, like in hydrogen peroxide would be HOOH. Hydrogen peroxide has the OO bond has a bond energy of 142 kilojoules per mole. So that's the minimum amount of energy required to break that bond. Is visible light capable of breaking the OO? Yeah, visible light is. In fact, red light is capable of doing that. Red light is capable of breaking this bond, so is violet light. So is any color visible light, because this is in the infrared region. Just need a high energy infrared to break this bond. And so this has to be protected from light. If you expose this to a regular light bulb, you're going to decompose your hydrogen peroxide. And so this is why hydrogen peroxide, when you buy it, it's stored in a brown bottle. Brown bottles are used to protect things from light. Like iodine. Is red light at 760 nanometers enough to break it? Well, red light at 760 is 157? Yeah, it's enough. So iodine, you have to protect this from all colors of visible light, because that would. How about bromine? Red light? No. So if you didn't want to use a brown bottle, what you could do is you could use a clear bottle, colorless bottle, and store it, but just change all your light bulbs. If you change all your light bulbs to red light bulbs, then your bromine will be okay. You know, you don't have to worry about it decomposing. But if you use a regular white light bulb, then you're in trouble, because you're going to start decomposing your bromine. At least, you know, this is probably probably green is enough to break this. Maybe yellow. Chlorine's a little harder to break. How about like a carbon-carbon bond? You know, we're full of organic chemicals like DNA. DNA has lots of carbon-carbon bonds. Is visible light going to break carbon-carbon bonds in DNA? No, we don't have to worry. I mean, I could just stand underneath the visible light and not worry about breaking carbon-carbon bonds. Actually, what kind of light do I have to worry about? And so let's do this. And so the next example is going to be this. What wavelength of light is required to break carbon-carbon bonds? We'll just say the average. We'll use the average is 347 kilojoules. So the energy of the light, the energy of the photon, is equal to h nu, which is equal to hc over lambda. So we solved this equation for lambda. Lambda is equal to hc over the energy of the photon. Well, the energy of the photon's got to be the energy of the bond. Otherwise, you know, if the photon doesn't pack enough punch to break that bond, then the bond's not going to be broken. And so let's say that the photon energy is less than 347 kilojoules per mole, the bond's not going to break. So we need 347 or greater, right? And so what we'll do is we'll just plug this in. H is 6.626 times 10 to the minus 34 joules. Joules times second, it's, you know, joule per second, we call that a watt, you know, how many joules per second. Joule times second is not a watt. A joule times second is called an action, unit of action. C is 2.998 times 10 to the 8 meters per second. And lambda, or actually no,
E is, what is E? 347? 347 kilojoules. We'll have to convert that into joules. 1,000 joules per kilojoule. So what do you get for the wavelength?
.72 times 10 to the negative 31.
5.72 times 10 to the negative 31 meters. So that's the wavelength we need. This would be what we call the maximum wavelength, because this is minimum energy. The minimum energy required is 347. And since wavelength and energy are inversely proportional, the minimum energy would give us the maximum wavelength. Any wavelength greater than this would be too weak, and so we need a wavelength of this or smaller. So that's max. Well, what kind of light is that? So let's take a look at the electromagnetic spectrum. We don't have to have the numbers memorized, it's visible light. And so if we go back to the electromagnetic spectrum, let's see what kind of light that is. Get a little wavelength here. Uh-huh.
Do you have to cancel the mold out somewhere?
We'll talk about that in a minute, but not necessarily. I mean, this is the lambda per mole. I'll talk about that in a minute, how that works. What is that? Energy. What kind of light is that? So when I look at this,
Below yellow.
well, it's 10 to the minus 31. So I got gamma rays here out to about 10 to the minus 16. Now the 10 to the minus 31 would be right around here. Around here. 10 to the minus 31 would be what kind of light?
No, it'll still be good.
Would it, well, it would be ultra gamma, or like a, let's say, a mega gamma ray, a mega photon would be it. And in fact, you know what it would be? It would be like the end of the world type photon is what it would be, because we're at the end of the electromagnetic spectrum. It would be the end of the world photon, because you're asking a lot of this photon. You're asking this one photon to come in and annihilate 6.022 times 10 to the 23 bonds, right? And so this is like one mega photon coming in and destroying a mole of bonds. Does that sound like it's going to happen? No, it doesn't work like that. You can't have, one photon cannot destroy a whole mole of bonds. You know that?
Oh, so I lose the energy.
One second.
Yeah, because what's going to happen is one bond is going to absorb. Can two bonds out here absorb one photon
No.
and then break both bonds? No, it doesn't work that way. And so this is what we call quantum yield or quantum stoichiometry. And so when we look at this stoichiometry, this is wrong, because this is a crazy, ridiculous wavelength, and this is why it would be end of the world, because that photon would pack so much energy it would destroy. I mean, if you could destroy mole bonds with that photon can cause a lot more damage.
But a packet of those.
Yeah, I mean, a packet of this would be, that's why I say end of the world, because if you had a mole of these photons, what would the energy be? And so if you had a mole of those photons, the energy would be a lot.
This is science fiction.
Yeah, this would be science fiction stuff. And so if we go back to quantum stoichiometry, let's talk, quantum stoichiometry is like this. Quantum stoichiometry is one photon is going to be absorbed by one bond. Like, it would be nice if I could use this mega photon I use this megaphoton, hit potassium, and eject a mole of electrons. So one photon comes in, hits the surface of potassium metal, and ejects a mole of electrons. Is that going to happen? No, I mean, that would just destroy the potassium. And so it's going to be one photon per bond broken, or one photon per electron ejected. It would be great if I could use one photon to eject 2 electrons, but that doesn't happen. This is what we call quantum yield. And usually we have to add more than one photon because the percent yield, it's like percent reaction is less than 100%. But we're going to assume 100% yield. And so in other words, this. So if I have a mole of bonds, I'm going to not need one photon, I'm going to need a mole of photons. And so the problem is the energy, and we have to keep track of all this energy stuff. And so what I need to do is, from here, let's redo the problem. I have 347 kilojoules per mole. That means one bond requires how much energy? And so I got to figure out, well, if I have a mole of bonds, then 1 mole of bonds contains 6.022 times 10 to the 23rd bonds. And therefore, I have to divide that by Avogadro's number. And then I'll get how much energy per bond is required. So, do that here. We'll get 347 divided by 6.022 times 10 to the 23rd.
5.76.
Yeah, 5.76. So this is 5.76 times 10 to the minus 22 joules. Well, violet will only give us up to about 3.8? No, 3.0, 3.1? About 3.1 times 10 is times 10 to the minus 22nd. I need to go to joules. So I'm going to go times 10 to the minus 19. So I know the number in joules. And so 3.1, well, this is more energetic than violet. And so where does this place it in? So now let's redo the lambda calculation. Lambda is equal to hc over the energy. And this is joules per bond. Right? And so I get 5.76 times 10 to the minus 19 joules of energy per bond. And so this tells me the wavelength of the photon I need for this, which comes out to what? This comes out to 3.447 times 10 to the minus 7 meters. Do you recognize that? 3.447 times 10 to the minus 7 meters? You probably don't recognize that unless I do something to this. 3.447 times 10 minus 7 meters is equal to 344.7 times 10 to the minus 9 meters. 10 to the minus 9 is a nano, so this is 344.7 nanometers. What kind of light is that? Well, violet goes to 390, and so this is past violet. It's got to be in the ultraviolet. This is UV. Ultraviolet. And so ultraviolet is enough to break bonds. In fact, it does it. Ultraviolet does this all the time. This is why you're supposed to wear sunscreen, right? Protect you from the ultraviolet. Even if the bonds do break in your DNA, there are repair enzymes that come and fix the bond breakage, because it's so common. It happens. Years ago, I was told that your DNA is cleaved 200 times a day. This was before significant ozone depletion. Now it's probably way more than that. But now everybody's wearing sunscreen, or a lot of people wearing sunscreen. So you see that. Is it time? Oops, all right. We'll stop here.
The ozone